Here we will be discussing telegraph noise, also known as burst noise or popcorn noise. Now, before you go and make yourself a bag of Blasto butter, you should know that telegraph noise is a great place to begin a study in any kind of noise, as it is easy to analyze and perhaps even easier to understand. Let's start by answering the question, what is telegraph noise? Simply put, telegraph noise is a binary signal of values 0 and 1. A typical signal will look something like this, where for each time step delta t, we use constants of proportionality r and sigma to represent the transitions from 0 to 1 and 1 to 0, respectively. The probability of making a transition is then delta t over the appropriate constant. As an exercise, let's consider the limiting cases of the system to gain a better grasp on what we are dealing with. Here, we have the case where r is much larger than sigma. What should the signal look like? Well, with a large r, we have a small probability of transitioning from 0 to 1. So every time the signal reaches 0, it should get kind of stuck there for a bit. So we expect to see a signal of mostly 0 with a few narrow peaks of 1. Well, what if the opposite were true? What should we expect to see then? Not surprisingly, the signal should look pretty much exactly the same as the last signal, just upside down. Well, what about the case when r and sigma are the same, or at least comparable? What do we see then? All we can say is that the signal will be a somewhat even variety of 1s and 0s. Well, and maybe in this case, crooked lines. Now we are equipped to start asking real questions regarding this signal. One good question to ask for any system of noise is, what does the power spectrum look like? A good follow-up question would be, can we solve for it analytically? While the answer is yes, we do need to introduce a new concept before approaching the problem, namely autocovariance. The definition of which being the average of the product of the signal at a time t and the signal at a time t plus dt. Now that probably sounded confusing, so all math aside, what does this really tell us? It's actually pretty intuitive, as autocovariance is just a numerical estimation of how an event was affected by a previous event. Take budgeting as an example. The amount of spending money you budget yourself this month is likely very dependent on how much you budgeted yourself last month. Thus, monthly budgeting has a high autocovariance value. And with that, we are ready to tackle the problem, strictly speaking. However, it gets a little bit involved. Solving the problem requires a differential equation, a delta function, a complex integral, and something called the Wiener-Khinchin formula, which leaves about as bad a taste in your mouth as the phrase moist loin ointment. Now, I won't stop you from trying the derivation, and in fact I've included a link in the description to a helpful paper, but for now, let's focus on the important part, the result. This derivation produces a result for the spectrum that goes by the following. A constant A multiplied by an inverse time constant, 1 over t, all over the quantity omega squared plus 1 over t squared, plus another constant beta, another constant b. The important thing to take away from this is the 1 over omega squared relationship that we should expect to see in any numerical simulation. Here I will use Mathematica for my simulation. Given the tools available through the program, I thought Mathematica was best fitted. So here you can see my specified r and sigma values. I'm using a random number generator, right here, to produce the randomness. I use this function to append 10,000 steps to my signal list. You can see it plotted right here. Now, instead of using autocovariance and the Wiener-Khinchin formula, I'm using physics' best friend, the fast Fourier transform. It accomplishes exactly what the Wiener-Khinchin formula accomplishes, but without the blood, sweat, and tears. Anyway, this spectrum resembles the 1 over omega squared relationship, right? Well, we can check the exponent exactly with a log-log plot. A best fit line reveals a negative 1.97 exponent, which is very close to what we want. Another interesting thing we can do is compare this result with the result we obtain from a random walk simulation, which is what I have here. A random walk is another random signal where at every point we choose a direction, up or down, at random. Here I'm using the explicit definition of the Fourier transform to give us a visual representation of what we are doing with the Fourier transform. Down here below, I'm doing the exact same process that I did before with the telegraph noise simulation, and we can see that we obtain a similar exponent of -2. When we think about it, there's actually quite a few similarities between the telegraph noise system and the random walk system. So it shouldn't surprise us that we find a similar behavior in the power spectrum. In fact, both of these signals fall under the same category of red noise.